The New Quantum Era,
a podcast
by Sebastian
and Kevin Roney. Hi, in our third episode of the New Quantum Era podcast, we've got a real treat. Our interview today is with David Mazziotti, a physicist and research team lead at the University of Chicago. He generously showed up with some deeply fascinating material for your consideration. Professor Mazziotti is a highly accomplished scholar, researcher, and mentor. This interview with David is a ringside seat on what we think is some of the most interesting recent research on molecular and subatomic physics are now being explored by scholars using quantum computers.
Yeah, Kevin, I agree. This is a great interview. I was really excited that David was willing to join us. I have known David since 2018. When he approached me when I was at IBM, asking for access to the 53 qubit machine for some research, which my leadership was very supportive of because it was very novel. And in fact, David was sort of the first person who suggested to me that these devices can be looked at not as suboptimal computation devices, but as really exotic lab instruments. And so he talks a lot about in this interview his experimentations for simulating exciton condensates, an exotic form of matter at the subatomic level on this 53 qubit machine and on subsequent machines that he's been working on as well, which I found really exciting.
Hey, and look, I just for our audience, I want to maybe underline this, Sebastian. I mean, I hope it's already clear that neither of your hosts, we're not formally trained in physics. We have a very highly ambitious goals around studying this material and delivering this podcast because it's out of our own, passionate and surplus curiosity. So, if dear listener, you actually are well trained in these topics in physics, I mean, welcome on board. Love to have your input, your remarks. But however, if you're also somebody like me or Sebastian, and you're more of an amateur and you're really dedicated towards hitting it at a deeper level than what's happening in the popular press, this is the podcast for you. I mean, we hope that if you're a fan of deep tech or interesting events in science history, or just very substantial forms of abstraction that could perhaps blossom into huge consequences for the world, this is the place for you.
Yes, and those with formal training, please be gentle with us when we make terrible mistakes.
It'll happen. No doubt.
It'll happen. Speaking of mistakes, a note about the recording. I messed up and with our recording software, and there were a little bit of extra technical challenges with actually assembling the final mix. So if the audio quality is not great, that's on me. I apologize. And I think there was also some construction going on where David was. So, but modern podcasting, that's just the way it works.
The way it is, man.
Yeah. And so, I mean, I'm very excited to bring this interview to our listeners because you could really sense David's got a very infectious sense of enthusiasm. He's very passionate about the topic. Obviously, he talks a lot about his journey to this career, which I think is always fascinating to hear. It's something I always ask researchers about, like what brought you here? It's such a fascinating place to be in terms of exploring the field at this point in time. And also, it's an interesting counterpart, as you pointed out, Kevin, like he's very optimistic about the possibility for breakthroughs in the near future, which is in contrast to some of our previous conversations with Cesar in particular, where we were talking about how we haven't even really had this transistor moment yet in our episode 2. And I think that's just a really fascinating contrast in the computer science lens, right? The computation lens. These are very noisy, flawed machines that can't really add very well because they come up with different answers all the time. And the scientist lens, where this is an extremely powerful, extremely sophisticated engineered device that makes possible some physics in the lab that has never been possible before.
Yeah, I think that's the perspective that I think is really the story beneath the story here. That, again, I don't think it's getting anywhere near adequate attention in the popular science press.
Awesome.
Well, look, I hope this interview reaches you, our audience, with the same way it did us. It was a huge thrill. And now on to our interview.
And we're live. Okay, so today we're going to be talking with David Mazziotti. And David, can you introduce yourself? You have quite an illustrious background, I think.
I'm a professor at the University of Chicago. In terms of background, do you want me to talk a little bit about how I got interested in quantum in general? Or okay,
sure, that'd be great.
So, I've been interested since probably grammar school and early high school. Like many, I just became fascinated about the idea of how what is the world made of, right? The idea of atoms, molecules. There's really, not much more exciting than that. And I'm recognizing just that, learning about the fact that atoms are made up of electrons and protons, was just super exciting. And thinking about how radiation interacts with molecules and atoms was something that just drew me in. The idea of the photon, the idea that that radiation is both a particle and a wave. That notion of duality just was something, so interesting. And on the one hand, it seemed so intriguing and yet so different from ordinary experience. Personally, I got really interested in science and chemistry and physics and so on because my dad was a professor at Columbia at Barnard College, the women's college for Columbia, in the early 1970s. And so he taught quantum mechanics and he had a PhD in theoretical chemistry. So in many ways, I ended up kind of almost like an apprentice, kind of inheriting some of the, excitement that he had for that. He himself ended up in the mid-70s deciding to go to medical school and pursuing a career in medicine. And so I think in some ways, when I was growing up in the early 80s, I would talk to him about science and he would always get so excited about it because I think in some sense, he wasn't in the middle of it day to day, right? But he still from that distance could really appreciate how exciting, it really is. And I had the good fortune of really working with just some great mentors, both in college and in graduate school. So in college, I went to Princeton University and had the chance to work with Herschel Ravitz, who is just amazing. And Herschel Ravitz is the expert of looking at quantum control of molecules, thinking about how radiation interacts with molecules. How can we use radiation fields to actually, for example, cause a chemical reaction to occur or, create a certain amount of yield of some process. And so, working with Hersch was just an amazing experience. He's one of the world's greatest mentors. And so that was a great experience. And then from there, I went to Harvard to work with Dudley Hirschbach. And Dudley is just incredible. He's just so excited about science and he brings it to life in a way that is extremely special. And so working with him was just an absolute pleasure. In addition to being just, so excited about science. He himself, did great science and he won the Nobel Prize in the 1980s for his research looking at crosses of beams of molecules. So for example, you take a beam of molecules and then a beam of another reactant. And you take these two reactants and you cross them together. And then you look at and see at what angles the atoms, and molecules scatter off. And by measuring the properties of the scattered products, you end up learning tremendous information about, about the chemistry of the product. And what's great about it is you see, I think in his work, this intersection, and also in Hersh Rabitz's work, this intersection of chemistry and physics, and just bringing ideas across science together. And I think that's, one of the great lessons about what leads to great science is this excitement about ideas that cross different boundaries and say, okay, let's take the greatest ideas from different places, bring them together, and we end up finding that we have a new perspective on science. So that's really, I'm really fortunate to have had great mentors to teach me and kind of bring me to to science in new ways and get me ready for for basically life after graduate school. I was a postdoc briefly in two different places. So actually not too briefly, I guess a year with Weitao Yang at Duke University. Weitao is known for basically being one of the developers of density functional theory. He's the Y in V3LYP functional that's used throughout the world for electronic structure calculation. So it was a great experience working with him. It was fantastic. And then from Duke, I actually went back to Princeton and spent a year working with Hersh Rabitz again on radiation and control theory. And it was after that then I arrived at the University of Chicago and started as a professor myself, and started a research group. And I also, can't say enough about just the atmosphere kind of with which I was received at the University of Chicago. There's my colleagues.
It's a great institution.
Just wonderful colleagues, and it's a great experience to get started there, and still loving it now for sure. So
then, when you took the professor role, was that in chemistry? Were you teaching quantum chemistry?
Yeah. So in some ways, it's kind of interesting, right? Because we're in this moment, Sebastian, where quantum has become so obviously important for a lot of different reasons, and we're at kind of new possibilities in front of us. But yeah, my interest in quantum, when I started at University of Chicago, it was in some sense quantum was part of the kind of theoretical chemistry portfolio, but it wasn't as like omnipresent at the university the way it is today.
And then David Oshlam came along.
That's right, exactly. A bit later, but yes, absolutely. And today, we're in a whole new era where David Oshlam built the whole quantum exchange, the Chicago Quantum Exchange, and there's just a tremendous amount of excitement now around quantum, of course, both at Chicago and beyond.
So when we first met, was that the first time you were using quantum computing hardware to perform experimentation, like simulation of quantum chemistry?
Absolutely. So that was our first foray into it, and our first paper was on thinking about using the quantum computer as an experiment to test something called the generalized Pauli constraint. And so the Pauli exclusion principle is sort of well known in general chemistry, and the idea is that an electron can occupy a spin orbital, but you can't put more than one electron per spin orbital or more than two electrons in a spatial orbital. And it's called the exclusion principle, and so it's excluded. And it's really the reason why, as Feynman kind of says nicely in his lecture notes, the reason why you can't put your hand through the table is because of the Pauli exclusion principle.
As fun as that might be, as a party trick or whatever, you probably wouldn't want to do it all the time.
That's right, exactly. But you can think of an alternative, another universe somewhere out there where maybe, we actually are not acting like what are so-called fermions. So electrons are fermions, and they have this property that they have to obey the Pauli exclusion principle. We could be that other set of particles called bosons, where maybe, we could actually
bosonic humans.
Right. So anyway, that we decided there's this notion of generalizing the Pauli exclusion principle, where if you get to even by 3 electrons, if you're in a pure quantum state, which means that you're in a quantum state that's just a single quantum state, not an ensemble, but just a single state, then there are additional constraints on what can actually, the occupations of the orbitals, what can be occupying an orbital. There are additional constraints beyond the Pauli exclusion principle, and these are called generalized Pauli constraints. And so what's really cool about a quantum computer is that it automatically generates states that are pure quantum states. So they should obey these generalized Pauli constraints. So our first foray into quantum computing was to take an IBM Quantum computer and just give it a whole bunch of random preparations and just do a whole bunch of measurements and see if we were obeying this generalized constraint or not.
Right. And that pure quantum state you're referring to, that would be at the individual qubit level, though, right? Right. Within the Josephson junction, that sort of construct.
Well, even collectively. So once we actually prepare the entire state on the quantum computer of all the qubits, if we have a perfect quantum computer, and that's the catch, of course.
Yeah,
if we have a perfect quantum computer, and we'll get to this later, right, without noise, then essentially we would have a pure quantum state. But in reality, actually, there is a bit of ensemble. There's a bit of non-pureness that comes in. And we were curious then, what would that do to the constraints and so on. But what we found is it ended up, there's a geometric object. And basically, for 3 electrons, the set that's actually supposed to occur is one size. It's a polytope. And there's another geometric polytope the same size that's forbidden. And we found that all of the preparations ended up in the allowed space, and none of them ended up in the forbidden space. And even at the boundary, when we prepared a point on the boundary, we tended to see a bit of contraction from the noise into the allowed space, but not into the other. And so that was our first paper. And I think what was interesting is it was one of those papers where we were thinking about the quantum computer in a very experimental way, even though we're not experimentalists, so it's kind of funny that way. But we were really thinking about, okay, we're going to use the quantum computer to prepare these states and learn something about quantum mechanics from the quantum computer.
And I did read just some of your papers before this. I'm not all that deep. I'm trying my best to be prepared. But I saw it covered the polytope. Was that the polytope you're talking about?
That's right, the polytope, exactly. Yeah, it's a beautiful picture, right?
Yeah, it's really cool. Yeah.
And we have all these colored dots that essentially are, those are the preparations. So all the colored points in there, those are the results of a quantum computing experiment. And we see them all lie in the allowed part of the polytope.
And what measurements are you doing inside the computer the quantum computer to register that data on the polytope?
Right. So basically what we're measuring is the 1 electron reduced density matrix. And that's the probability distribution for essentially the orbital space, seeing how many electrons are in this orbital or that orbital. And then by diagonalizing this 1 electron reduced density matrix, we end up with the orbital occupations that allow us to test the generalized Pauli constraints.
And is that you're like looking at the large valued eigenvalues? Is that one of the components of the search?
So we just look at the whole the constraints themselves are actually written in terms. So it's a great question. The constraints are written in terms of the eigenvalues or the occupations of the orbitals. And so we have to put in all 6 or all, no matter how many orbitals we have to put in the occupations of the different orbitals. And there's an inequality. And so we don't want that inequality to be violated. And the inequality corresponds to one of the facets of the polytope. So a polytope is basically a convex object with a bunch of flat sides. And on one side, there's this polytope that's forbidden. On the other side, one that's allowed. And then there's this hyperplane in the middle called the Borland-Dennis inequality. And you just don't want the points to go through.
That's really fascinating. What struck me about what you were doing on the IBM hardware a couple of years ago now was, you're doing these very sophisticated simulations on hardware that's, I talk to quantum chemists pretty regularly, and most of them go like, well, I can't really do anything with it until I have a fault tolerant qubit, right? Come back when you've got fault tolerance, basically.
Right. Call us back at that point.
Yeah.
It could be a little while. It could be a wait. Yeah.
That's a good excuse, right? I'll call us back in a while.
Exactly. Well, I was just really impressed with how creative your approach was, because you're using this limited hardware with limited capabilities from a gate perspective, from a noise perspective, but using it in this really creative way to do really sophisticated simulations. Where did that inspiration come from originally? Do you remember?
Yeah, I remember contacting you, and we were kind of desperate at that point. We were thinking about excitons, and at the same time, we were very interested, and we're still very interested in this idea of, one of the themes that just traces through all the research we've done is a fascination with strongly correlated quantum systems. And how do we deal with situations when the electrons are highly correlated with each other? And that's challenging because one can't use mean field equations then to describe the chemistry and the physics. And so this whole regime of many particle quantum mechanics, but particularly how it relates to chemistry. And excitations or excitons, an exciton is a quasi-particle of a particle and whole. And the idea is there's a literature that discusses how one can take a whole set of excitons and potentially prepare them in a coherent state. Now, the best way to understand this is actually to think about something that we're more familiar with, which is superconductivity. So in superconductivity, electrons form Cooper pairs, and these Cooper pairs of electrons all end up in a global quantum state. And that allows you to send electricity into the superconductor and actually have a current then come out, a macroscopic distance away, but not have any loss due to friction, because you're really sending an electron into a global quantum state that's entangled with the electron that's coming out on the other side at the same time.
Yeah, these swarms of these Cooper pairs, like oscillating back and forth. I mean, I gather as a quasi-particle, they have an isomorphic quantum state comparable to just the up-down spin electron. And so, and so it's just amazing. We're relatively new to the subject, and so we stumble across these truths, and it's just a marvel of amazement. It's perhaps old news to you, but we just learned that a couple months ago.
Well, no, I think I totally agree with you, Kevin. It's just, it's something that the power of quantum mechanics is something that's always fascinating, because it defies what one thinks about, classically, and you wouldn't expect something to have superconducting properties. And so a superconductor, of course, has these strongly correlated electrons, and excitons, in principle, could also be condensed into a global quantum state. And then exciton condensates were something that were harder to realize. And so it's only after 2000 that people were able to realize exciton condensates by pumping them with light, with radiation. And then in the last few years, since 2017, they've been able to prepare them in the laboratory, even without pumping them with radiation, either using strong magnetic fields, or actually in some cases not using any magnetic fields at all, but using creative chemistry to build, for example, van der Waals heterostructures, like essentially a two-layer stack of material, where they can get the particles and holes to essentially line up kind of like a chessboard or a checkerboard, where the particles, the black and white squares are like on top of each other. The particle and holes are, you can kind of visualize them on top of each other, and you get a macroscopic number of them kind of all lining up in a condensate. And then we were thinking, well, that's, it's so fascinating, the idea of condensation and this exciton condensation. And we've been thinking about how to potentially prepare that in molecular cases. And with a quantum computer, what's really neat is an exciton is very similar to a qubit. So the very fundamental unit of a quantum computer is this qubit, which is either in the down state or in the up state. But that's a lot like an electron being either in the down position and so it's isomorphic between the exciton and the qubit. And so if we can then actually think about an exciton condensate is similar to basically preparing the photons that are exciting these qubits in the superconducting qubit quantum computers, let's prepare all of these qubits in a global quantum state, or an exciton condensate, or a qubit condensate. So that's what we just sort of ended up going in that direction. And we realized that we could do the preparation in a compact enough way that if we had a 53 qubit quantum computer or more, we could go ahead and explore that. And so I think we did it initially up to 16, and we just thought, this is fun. We're having so much fun.
Might as well keep going.
Exactly. We don't want the party to be over. So that's when actually Sebastian and I got introduced. I talked to my colleague Dave Schuster down the hall, and I said, "Well, who can I talk to?" And
to give me the
I have the right
big
person to talk to. And so I wrote to Sebastian, and
the hardware
and
man
Sebastian came to our rescue. Absolutely.
So amazing. And so, David, I mean, some of us are just fascinated by these topics of this deep theory. I mean, it's very entertaining. There are other members of our audience who are more into applications. Could you help, for those members of the audience, ground us? What are the major, engineering or commercial applications of some of this research? It would just be helpful, I think, to give it some more context.
Sure. So why are we interested, right? So the quantum mechanics is cool, but what would the applicability be? Like, why would we want an exciton condensate rather than just obviously it's fun to do, but what could it be useful for? Well, I think the best way is sort of the analogy with superconductivity. So superconductors can, in principle, give us frictionless flow of energy, of electricity. So Cooper pairs can flow through a superconductor, and we know that one of the properties, in addition to like magnetic levitation, one in principle can have frictionless flow of electricity. In the same way, the exciton condensates give us the analog in energy. And so exciton condensates in principle could give us frictionless flow of energy across the material, because we can pump a photon in, create the exciton, and actually have then the exciton de-excite and release the energy on the other side of the molecule without any frictional loss in principle.
Huh. And so possible application. I mean, I don't really know the material well. I was just scanning material to be prepared for this. So please forgive me if this sounds ignorant, but it sounds like photovoltaics or semiconductors, maybe some of these new applications in graphene. I mean, there could be a world of new applications right on perhaps new silicon chips or new solar generation systems. Is that the right neighborhood, do you think?
Absolutely. So it's still early days. Exciton condensates are still a frontier area. And part of it is it's only been realized in a small number of systems, but the temperature at which it's being realized is slowly going up dramatically. So initially it was realized down essentially at the millikelvin range, but now we're talking about hundreds of Kelvin. And so if we can bring that up to room temperature, then it becomes something that we end up with molecular scale devices, so nanotechnology, but we could actually build potentially some devices that would go into other and be frictionless, in their energy transfer. So I think doing that over a large distance would be very science fiction still, but we're getting closer to the point where one could conceive of building materials that, would benefit from these, highly energy efficient transfer, from one part of the molecule.
And how you're perhaps anticipating the same kind of road of progress that superconducting materials made. I mean, they're up to, I gather, room temperature, so to speak.
Right, getting closer to room temperature. And there's a belief that exciton condensates could be even potentially more successful than superconductors, because the binding energy of the exciton is larger than the binding energy for the Cooper pair. So it's a little bit more robust to increasing the temperature.
Ah, okay. Interesting.
Because you won't essentially have the exciton, break up. The way the Cooper pair, the reason why you end up losing the superconductivity is the Cooper pairs, start to break apart, at the higher temperatures.
Probably the underlying problem with coherence in quantum computing. Is that accurate?
Yep, okay. Yep, exactly. Yeah.
Wow, that's so interesting, man. So this is really an early stage on some big breakthroughs. And it's just amazing that, there's all these very exotic and complex experimental methods that you would want to perhaps try to do for producing these exciton condensates, but you did it on a quantum computer. Wow, just from your desktop, sounds like, right?
Right. So the quantum computer, gives one an ability to look at some things that before were really more just a theoretical dream. You would say, okay, let me, think about this strongly correlated system, but to be able to push it. And so, I think our work is part of a constellation of cool experiments that have evolved over the last couple of years on quantum computers. And so we've seen a number of really cool stuff produced. For example, something called many-body localization has been achieved on quantum computers. A recent article on achieving a spin liquid on a quantum computer. So I think, the exciton condensate is sort of part now of a family of exciting science that's been of strongly correlated systems that are being modeled on the quantum.
And in fact, you've collaborated with Sabri Kass and Pri Narang and Katie Head Marsden on a couple of papers on sort of a generalizable system for simulation of open quantum systems, right?
Right. We just had Sebastian, we just had a paper come out in PhysRev Letters, I think right at the end of the year. And that's with Pri Narang at Harvard and Katie Head Marsden. And my graduate student Anthony Schlimgen and also Leanne Sager. So a bunch of us got together, and we were basically we're interested in open quantum systems, which are quantum systems that are exposed to the environment, and thinking about, okay, how what happens when you take a quantum system and you don't have a closed quantum system, but actually one that's connected to an environment. So the bath will push energy into the quantum system and extract energy from the quantum system. And these are particularly difficult to model in traditional classical physics and chemistry. because basically you're trying to deal with the fact that not only are you modeling the system itself, but now you have to somehow model the bath and deal with, the transfer and all of that.
And that comes for free with a superconducting quantum computer.
Yeah, so for a quantum computer, so on some level, one of the things that's really attractive is a quantum computer has noise in it already. And so that's one direction, is potentially to exploit that noise. So we've kind of been going two different tracks. One is to think about how do we model, how do we model essentially these open quantum systems on a quantum computer, not really thinking so much about the quantum computer's noise itself, but just trying to do it on a quantum computer. It's a bit challenging because the quantum computer wants to create closed quantum states. It wants to have pure quantum states. And so we have to do some tricks to think about how do we create time evolution that now is true for an open quantum system, because it's not going to be what's called a unitary evolution. It's something called a non-unitary evolution, where essentially energy is being lost and then coming back again.
So I was really intrigued by that very question in the prep I was doing. I mean, so on a classic quantum computer, I mean, that their whole vocabulary of coding elements are unitary transformations. For these open systems, is there something you can do on a standard quantum computer to simulate these open systems, or do you need new hardware?
It's an interesting question, right? There's always I guess that's another, going back to Sebastian's comment before, one could always say to the person developing the hardware, please give me new hardware, right?
Exactly,
can't do anything until you give me new hardware. But you can actually get around the issue. And there's basically a kind of a series of papers going back to the beginnings of quantum mechanics with people thinking about how would we get around this. We were following work from Sabri Kais, our colleague at Purdue University, and he came up with a clever way of using something called the Nage dilation, the Nage dilation. And the idea basically is that you basically take the unitary propagation you take the non-unitary propagation that you want to do, and you embed that in a larger unitary matrix. And so you dilate your space. And by dilating your space, it turns out just by one qubit, and so you have one ancillary qubit to dilate the space, and that's enough to actually transform your non-unitary operator into a unitary one, and then you can perform your unitary propagation. And so Sabri introduced this idea, and then in the recent work with Pri Narang at Harvard, with Kadai and Pri at Harvard, and my students Leanne and my postdoc Anthony, who is the head of the paper, we were generalizing this to some other ways of thinking about how we could dilate the space to propagate it. And so it's a fascinating question. And I think right now we're at a crossroads where I think there's a lot of excitement right now in the field for thinking about how do we use quantum computers to deal with open systems and do this non-unitary evolution. So I think we're in for an exciting couple of years to see what happens next.
Really interesting, because of course there's a whole bunch of new quantum algorithms out there, and many of the people watching this space are watching that very area with intensity, because of course there's all these huge breakthroughs. I mean, black swans, the potential's there all the time. Is it possible for you to speculate? I mean, could there be, for some of these techniques where you're using this dilation effect, with respect to doing inside a standard issue quantum computer, that there will be brand new algorithmic breakthroughs for classical optimization problems? Because those sound like interesting and exotic techniques.
I mean, there's definitely room for, I think that's that's for sure, that basically we are at a moment where it's almost like a tipping point, right? We don't really know the moment when something, some new emergent technology, some disruptive technology can come out and just shake up, the conventional, the conventional status quo. We kind of think
it feels like there's something on the horizon, doesn't there? Yeah.
Right. There's something coming. And, quantum mechanics has always been that way from the very beginning, right? I mean, its origins was one of people thinking that the world was sort of fixed. Everything was understood between classical mechanics and your electromagnetism. And then, of course, quantum mechanics emerges, and we suddenly have this notion that the energy is actually discrete and not continuous, with no real classical understanding, of why that should be the case. And then the profound, for chemistry, realizing that all of chemistry is really a consequence of this quantization of both energy and matter. And so today, I think that with the quantum computing, there are just, possibilities there, because we are able to now use quantum mechanics to prepare quantum states, directly on the hardware, whereas before, we're always trying to simulate the quantum mechanics on a classical machine, which has all sorts of. So I think that definitely possibilities are there for big growth. I think one of the things we're really excited about in the last couple of weeks has been some work that I've been doing with Sabre Kais, and we recently published a new paper in Communications Physics talking about what Sebastian was referring to before, this idea that maybe we could use the noise in the quantum computer as a way of pushing the envelope forward for dealing with open quantum systems. So the idea there is that, well, the quantum computer is already noisy, and we're often just trying to always put the fire out, right? So we're like firefighters, always trying to get the fire to go out, to say we want, and as we said earlier, somebody will say, well, give me a fault tolerant quantum computer and I'll give you the world, right? But can we make progress essentially with noisy quantum computers? I think that's one of the central questions. I would say that maybe in some sense that's maybe one of the pivotal questions, that we're bringing up tonight, because ultimately quantum computers are always going to be somewhat noisy to some extent. And I think we'll always go through phases of, well, it's not as noisy as it was before. But then, we kind of see that, right? Computers are fast, but then they get faster. And you're like, well, it seems like the old computer from a year ago was a little slower than the computer now. But, if we compared that to 10 years ago, right, it would have been fine. And so I think with quantum computers, the question is, how do we actually exploit the noise for benefit and gain?
I mean, that's a really novel thing you're bringing up here, is that so many people talk about the NISQ era, of quantum computing. In a certain sense, how to design algorithms will be resilient enough, given the noise, to still survive the computation. But what you're saying is that it could be actually a superpower, not just a problem to avoid.
Right, Kevin. I totally agree. I think it could turn out to be one of the more interesting things about quantum computers. I think we're also in a moment where we have to recognize that we don't really know entirely what a quantum computer is going to be good for in the future. So we have to be really open-minded. I have a feeling that it's going to be useful for a lot of things that we don't anticipate now. And so one of those things might be actually exploiting some of these superpowers that are almost hidden in the wood, sort of hidden, right? They're there in plain sight. They're hiding in plain sight, but we have to figure out how can we best utilize them. So Sabre and I were talking about this one day. We were just, we had really wanted to pursue some project on the noise. And we just started talking, which is the best way for science to emerge, right? You just, you have a conversation, you're just thinking about, what can we do to push the envelope forward? And we jointly came up with the idea that, well, what's cool about quantum mechanics is that if you prepare a quantum state in a stationary state, it stays there forever unless it encounters some noise. And so if we actually just prepare a quantum state in some excited state, and take a quantum system like a molecule or something and put it in an excited state, so think of a kind of a simulated molecule, we put it in an excited state, and then we know what that should do. It should do nothing. But remarkably then, as soon as it does something, as soon as it starts to evolve in time and start to, for example, decay out of that state and go into the ground state, we start to learn about the noise on the quantum computer. And we can do something really cool where we can do a form of very kind of elementary spectroscopy. So the way spectroscopy really works today is you basically kind of just sort of, you basically hit a molecule with radiation, you get it all excited and you watch it evolve in time, and then you do a fast Fourier transform and you figure out all the frequencies that the molecule can experience. But you also could go back to the early days of spectroscopy where you'd hit the molecule with a specific frequency and see how it would behave. And then you go ahead and you hit the molecule with another specific frequency and see how it would behave. So we did sort of poor man's spectroscopy, and we said, okay, let's take a quantum computer and we're going to take, let's think of two levels. And we have a certain amount of basically energy separating, photon to go from the ground state to the excited state. So there's a certain frequency of radiation required for that excitation or de-excitation. But we can also move those levels arbitrarily on a quantum computer. Unlike a molecule, we can just tune that level wherever we like. And so what we did is we basically modified our molecule to just tune essentially the level for the energy that would come out in the simulation. And then we would watch it, prepare it in a stationary state, and see how would it relax when we tune the molecule to have a certain energy for relaxation. And if, for example, the bath has a lot of energy, or the bath meaning the quantum computer's noise, has a lot of photons that are in the vicinity of the particular molecule that we created at the moment on the quantum computer, then we would actually see the excited state not stay stationary and come down. We might see, for example, some non-Markovian behavior where energy transfers into the simulation and then transfers back out again and then comes back in again. And so we ended up getting a spectroscopic fingerprint of each of our IBM quantum computers on which we were doing the experiment.
Wow. And so this it's blowing my mind just hear you say that phrase. But in more applied detail, what do we derive from that spectrogram of the QC?
People have obviously think about noise on quantum computers, and there's all sorts of benchmarks like quantum volume and different T1 and T2, different metrics for how accurate a qubit is. But I think the difference is it's a little bit like if you're trying to understand how kind of a car works, and you were to take apart all the different pieces and inspect each one and then say, well, this car is going to be better than that one because it's got better wheels, it has better transmission or whatever. And so in the same way, I think when one sort of looks at the specs about an IBM quantum computer or any quantum computer, you're kind of reading in about, well, how good is it doing, this part's this good and this part's that good. But we wanted to think about noise from the perspective of the program running on the quantum computer. And so the question really isn't about how much noise is on the quantum computer, but how much noise does the program running on the quantum computer see? So what we're really doing here, and this is, I think, what's innovative about our paper, is that we're saying, well, let's sort of be inside the program and sort of think about the fact that, okay, if we can now, we're not really trying to measure how the hardware is noise, but we're trying to say, well, if our program is simulating a system with this actual gap, because we don't really have the system in there, it's just a program, but by actually changing the molecule that we're simulating and changing the gap in the program, we end up seeing how the program couples to noise in the outside, and we get a spectroscopic fingerprint from the perspective of the running program.
I see. And that's a much more relevant and powerful diagnostic for the performance of the system. Yeah, that's really cool.
And David, are you doing that at the pulse level? Are you actually programming the pulses, or are you doing it with gates?
So we're doing it with gates, but we have to be very careful not to have the gates compiled. Otherwise, we can lose. So we had to be very careful to use gates that would not end up getting recompiled into something where we would essentially not get anything meaningful about
that. Because the compiler does optimizations that you don't want, or? Mm-hmm. Oh, yeah, I see.
Yeah, so it's essentially a process of simplifying the gate structure so that you would think you'd be measuring this, but you'd actually and then you actually don't see any relaxation. Like you just see the system kind of just be perfect because the computer is almost like thinking about the fact that, oh, well, you're not really applying a gate. So we have to make sure we're actually applying pulses associated. But we could do it at the pulse level as well, and that would be a similar experiment. It would give us more control over, what we're doing.
Yeah, Rigetti actually has a verbatim execution mode, which I think would support what you're describing quite well, because you literally tell it, don't do anything to it. I want you to do what I'm actually telling you to do.
Do what I say.
Yeah. No optimization, please. And the fingerprint, as you put it, is that like a qubit by qubit sort of data set? Like it varies by qubit?
Well, it's holistic in the sense that it's telling us about all the qubits that are running in the program. But we could have, for example, a computer with 10 qubits, and maybe our program only runs on 2. So we can actually run it on 2 different qubits and end up with a whole bunch of different fingerprints for, how would these qubits work in the computer versus those? But we're getting a sense, as Kevin alluded to, we're getting a sense of how noise is important to the problem as a whole. And we're hoping that can kind of inform a new way of thinking about quantum computing, at least as far as maybe noise as a quantum resource rather than as an enemy that we're, trying to always eliminate from the quantum computation. Because potentially we can use fingerprints like this as a way of error mitigation. So we could use it as a way of facilitating kind of putting out the fire and getting rid of the noise. Or we might be able to use it as a way of thinking about, well, if this is the noise on the quantum computer, we could now simulate open quantum systems that are subject to the same noise for free.
Yeah, I mean, random number generation on classical computers is a huge buzzkill for a lot of optimization algorithms, and so having an access to real randomness, hard randomness, without constraint, that actually could be a superpower. But you need to know those statistics with respect to the performance of the system.
Yeah, what the bath is and what would that do. So, right. So in principle, the quantum computer and its environment in which it is, could and I think just being able to have a more holistic perspective on the noise could be the way in which we're able to control noise better rather than trying to think. And it also gives us a way of benchmarking quantum computers is the third category, I would say.
Yeah, that's so powerful. Yeah.
You could kind of run it and see, well, how does this program kind of simulation work? And that's important for chemistry and physics, where you don't really care so much about, and I think it's this thing you kind of learn as you go along, because you kind of, you work with your students and your postdocs to kind of run stuff, and you get this sense after looking at the data that sometimes the computer that was supposed to be the biggest winner, doesn't actually work as well as the little engine that could ends up defeating. It's like David versus Goliath, right? The little engine that could ends up doing it. And I think part of that is because we don't have a great understanding of how all the errors kind of work together collectively. And as we build more sophisticated programs, the idea of looking at noise from a program level perspective becomes even more powerful. I think one of the things that one can kind of recognize is in the beginning, one can also come up with programs that are fairly simple and not so different from, let's say, an individual diagnostic. But as the programs get more sophisticated, not only do they become more kind of even more clever reporters on the noise in the system, but they also kind of end up giving us even a more bird's eye view of what's happening.
But also, just the brilliant thing about that research is that it opens up a huge array of applications on the ground floor for different vendors, right, of QCs, to give a level set comparison with respect to a broad diversity of dimensions of evaluation for noise response.
Yeah, we're really interested in that. That's a great point, Kevin, because I think there's an opportunity. And so one of the things that we're interested in taking a look at too would be to, for example, look at, for example, how does an ion trap quantum computer do on this type of experiment versus a superconducting qubit quantum computer, and that's the kind of thing that, could be done quite well with, some of the resources that are out there today. One can really, you can basically run different types of quantum computers against each other.
Or even reveal that, some classes of some QC architectures are great for, say, this class of problem, I don't know, Grover's algorithm, and some of these other ones are really great for I don't know, molecular geometry because of the different responses on the noise at different levels of energy.
Right. And it might give us some perspective as to, well, can we, how do we deal with that? How do we think about that? How much error can we tolerate within the simulation, to get information that's viable.
Wow. Yeah. So many cool foundational issues here. Yeah. Just amazing.
I was going to ask, actually, you brought up trapped ions. So all of this work has been on superconducting hardware so far. How applicable do you expect it to be on trapped ion? Or there's now, there's neutral atom or Rydberg atom systems that are coming out in the next year or so, and hopefully photonic systems down the road. I'm just wondering, how do you think it'll be implementing some of these approaches on those other hardware platforms?
Right. So Sebastian, I think it's going to be very applicable. It's fairly agnostic to the architecture. So I think in some ways it will be really fascinating to do some, architecture comparisons using, for example, even just the systems that we have in the communications paper, in the Nature paper, just basically looking at, comparing one architecture versus another, almost like a competition, right?
And one yardstick that you could use fairly to compare them all. Just amazing. Yeah.
Right. Just to see what happens, and also to see what the fingerprints look like. How much does it vary by frequency? And we did see tremendous differences. Like the simulation was much more sensitive to some frequencies than others. Does that continue essentially in other architectures? So there are a lot of interesting questions that would be pretty fascinating for sure to take.
It also, I wonder, do you think there's a lot of the language you're using is making me think of quantum sensing devices, which are meant to be sensitive to particular elements in the environment. Do you think there's anything applicable in that kind of direction with what you're doing?
I think so. I think it's still kind of early days on that. It's something that I'm really quite interested in right now. Actually, we haven't quite, I think, I think Sebastian, you're kind of framing it nicely. It's something that, we're still in the early days of thinking about. But, one of the questions is, I mean, I don't want to say it in a way that sounds dismissive of quantum sensing. Quantum sensing is an amazing subject with just amazing progress. But there's some level where, because it sounds like a little funny, but on some level, you can almost look at a quantum sensor as a type of little quantum computer, right? Not to belittle the sensors, but
Well, I mean, you mentioned Schuster earlier in the conversation. He is using Josephson junction devices with a strong magnetic field to try to detect dark matter, I think, is if I'm correct about this. So, yeah. So, I mean, it is a quantum computer. It's just used for something else.
Yeah, so Dave Schuster is doing amazing work and looking at all sorts of different possible ways of using these quantum computers in just totally novel perspectives. I think that's really some of the stuff that I'm saying where that's breakthrough work that's not kind of changing the paradigm of how we're thinking about using them. That's who would think, right? Dark matter being detected, potentially, by using a quantum computer. that's pretty amazing. So I think that's possible, that the quantum computers could be, open up some real new possibilities for it. And so, but it also is the other way around, where quantum sensing may inform how we think about what do we want to define as our quantum computer.
Right. Well, and this work you're doing around noise characterization, but even more broadly, like simulation of open quantum systems, it's almost mapping out a territory. It feels somewhere in between those two in a way.
That's right, exactly, because you're really thinking exactly about it's the physics and the chemistry and the quantum information kind of merging together in this special spot where we're like, okay, there could be, some real opportunities for advancement here. I would even pitch it further that, we could potentially, think of applications that have medical, or biologic applications as well.
Yeah. It's also striking how closely what you're doing adheres to Feynman's, whatever the catchphrase from the keynote from the 1981 conference, like nature is quantum systems. So if you're going to simulate nature, you're going to need a quantum computer. Like that's exactly what you're doing.
Right. We're really getting to the point where this is becoming possible. And so I think that's really where it's going to be interesting to see what happens in the next couple of years for the quantum computing, because, it's fascinating that perhaps we have to take some lessons from nature, even in thinking about what's the evolution of the quantum computer, what are going to be the uses, how can we use this, effectively. But I think the applications are going to be, numerous and really exciting. And I think it'll be very surprising too. So we'll just have to see where the science leads us, which is always something, I think super exciting about the frontier, is that even as much as one looks into the crystal ball, it can be difficult to prognosticate precisely, where we're going.
Well, we're so rooted in what we've experienced before, right? I mean, if you look at quantum computing, there is a very evident sort of impulse to try to cast it in the sort of paradigm of classical computing, and that might work. We might get there and get to a quantum computer that operates in the way that a classical computer does, at least on the surface, with very different mechanisms internally. But it's also entirely possible that we end up, Kevin and I have talked about this before, sort of revisiting and reinventing like an analog approach to computation or information science, because these are at their heart really analog devices in some ways, right? I mean,
right. And they're interfaced with analog devices now. And so really, I think we think a lot about how can we use these quantum computers as, as accelerants essentially for speeding things up, and I kind of think of actually a funny story. It's kind of a little tangential, but as a kid, basically we were always fascinated by having faster computers, right? And so there was a time when you could buy a coprocessor to sort of speed up the 486 to a 586. So maybe some of the members listening to the podcast might kind of remember this.
Yeah, that's for old people, what you just said.
The older generation, right? Those who kind of remember, war games and things like that, with Matthew Broderick. But basically, you could speed it up with a coprocessor. So you would put that on, and it would speed up the calculation. So in some ways, the quantum computers are kind of like these coprocessors, but it's a delicate process, right? You got to be very careful how you essentially use the quantum computer to speed it up. So I remember we had a coprocessor where, we put it on the chip, and it was kind of a warning, like, do this at your own risk, right? Because it wasn't, it was amazing, actually. I remember it was like funny, this kind of like this bird would come up at the beginning of what it was like a symbol of the coprocessor. And then suddenly it'd be like flying through this, it'd be just like, wow.
Right. It was
like
piggybacked on top of the leads of the
Yeah, you
of the
literally
CPU.
like put it back, like, don't try this at home kind of thing.
Yeah.
You literally like put it on top
Intel
of
does
the
not
chip.
approve.
Not approve, right? Exactly. Don't do this, And so you put that on and suddenly the computer would just be flying along. And you're wondering, like, how does this work, And I remember, like about 2 months into that, the whole thing burned out, right? And then suddenly the chip was running slower than ever, So I think
halt and catch fire. There you go.
So right. So there's a lot of power, but one has to figure out, how to use things in the right way to really exploit that power for, essentially speeding up calculations.
There it is, right?
In the right way.
So it's such a fun time to be alive. Hey, David, it's been a really fun conversation. Maybe this is a little bit too forward, but if there's any listeners who want to mess around with some of the code, and are qiskit literate, is any of the stuff that you've mentioned here, perhaps available open source style? They could just, I don't know, download a little sample and get a taste, even if they don't know the physics so well.
Right, Kevin. Great question, actually. Yeah. So actually, on our page, basically mazziotti.uchicago.edu, you can go there, and on our software page, we basically have a link to our GitHub, and on the GitHub, we actually have the tools for sort of doing some of the simulations that we've developed a new approach for kind of the variational quantum eigensolver is one of the established eigensolver techniques for for simulating of course for simulating molecules on the quantum computer, and we've developed some tools for doing what we call contracted quantum eigensolvers. And it's a way, basically, it's an alternative to the VQE, the variational quantum eigensolver, which really has few variational parameters, because what we do is we project the Schrodinger equation itself onto, essentially project the Schrodinger equation itself onto the space of two electrons. And then what we do is we use that projected Schrodinger equation or contracted Schrodinger equation to figure out what's the next sort of step to take on the quantum computer to improve the wave function. And so it becomes a very natural process, because the very contracted Schrodinger ends up giving us a residual that we can calculate. Sort of we measure, we prepare sort of, we take the residual, we move the state forward on the quantum computer, we do some tomography to figure out the new state, and then we basically automatically, get it. We can automatically then measure or compute a new residual to figure out what's the next preparation to move forward.
Wow.
So that's something that we have a package that my graduate student, Scott Smart, put together, and that's on the GitHub. And it kind of goes through the whole process of setting up a calculation with a contracted quantum eigensolver.
Wonderful. Yeah, that just sounds so inspirational. I mean, it sounds like it's a big breakthrough with respect to many interesting experiments that you do. But I mean, lots of VQE algorithms have been retasked from molecular geometry into optimization problems. Maybe there's some future algorithmic breakthroughs along the lines of Metropolis Hastings that you guys are pioneering.
Right, there could be some cross-pollination for sure across other areas, but yeah, we're really excited about this way of thinking about it, because oftentimes, the usual approach is to kind of variationally solve an eigenvalue problem on the quantum computer by moving parameters, but this approach kind of takes a perspective, a different one, where we build on some of the research we've done in my lab on something called reduced density matrix theory, and the idea basically there is to exploit the fact that the electrons only have pairwise interactions. So because of that, we can use contractions or projections of the Schrodinger equation onto the space of two electrons to kind of accelerate our simulations, either classically doing classical calculations with reduced density matrices, or on the quantum computer. It also turns out that that's also a very powerful way of accelerating simulations, because one gets this contracted information is kind of precisely what you need to guide the state to give you the observables that you need essentially that you're kind of targeting, whether it be the ground state or other energetic properties of the molecule.
Amazing. I mean, I've got a thousand new questions coming to mind, and we're running out of time. Maybe we need to. Do we need to cap it now, Sebastian? Or?
Yeah, probably. I mean, I think from the perspective of a reasonable demands on David's time, but also reasonable length of podcast. But maybe we can tee up a part 2 later on, David. I agree.
That'd be cool. That'd be cool. Certainly, we'd be happy to be a guest in the future again. But I've had a fantastic time tonight.
I'm glad, David.
Well, if I can close out, you mentioned like demanding new hardware as the easy way out. So maybe to close is if you had your magic wand, you could wave it and wish for any new hardware in the next year. What would you want? What would how many qubits? What kind of qubits? What kind of characteristics?
Well, yeah, I think that actually a system maybe with, I mean, it's hard to say, right? Because it's kind of like, that's a hard question, Sebastian, right? That's like asking, what would you ask, what would you ask Santa Claus for?
Right.
If you could have, anything. I certainly think, I think the noise is so important. So I do believe that probably a system with higher fidelity would be my first ask in terms of hardware. I think that having a system with less noise would open up some really exciting possibilities. So let's say a computing chip with between maybe 50 and 70 or 80 qubits with really high fidelity, that would be a really cool thing with which to work. I think that would be awesome. And of course, I think we're getting closer to all sorts of things. And so
yeah, we're definitely in that range. There's multiple vendors in that range, and the fidelities continue to slowly creep towards the green zone.
Right. I mean, just a follow up on that, on the point there, it's kind of funny that I think that, and I was talking to Sabre Kais about this as well, and he and I were just saying, well, it's amazing that everyone a couple of years ago, and Sabre has a lot of perspective. He's been in this, in the quantum computing in chemistry longer than myself, and he was saying, well, it's funny that a couple of years back, everybody was saying if we only had 50 qubits, to conquer the world. And of course, we have 50 qubits now.
50, so now what? Yeah.
It'd be great 1,000 qubits.
Exactly. So, but I mean, he was saying that now, it's an issue of, it's the fidelity is really the important question. And, we really need to be able to create 50 qubits with enough coherence. And so, one of the things I'd be really keen to see is if we had such a computer, we could revisit, for example, our exciton condensate calculations. And in those calculations, we have a metric for how perfect our condensate is, relative to what we could potentially generate with no noise. And so we have a measure of the noise from the amount of coherence in the condensate. And so it'd be very exciting to revisit those calculations and see, how much more coherence could we get, if we were to, to essentially go.
Sounds like a benchmark.
Right. Exactly. A benchmark for that. So I think there's a lot of cool stuff, and again, we're basically putting some of these things up on our GitHub page as well.
That's great.
So
yeah, we'll post the link when the episode goes up for sure.
Awesome.
Okay, cool.
David, thank you so much for your time. This was just
thank you.
Such a joy. Good time.
Well, Kevin and Sebastian, thank you so much as well. This is fantastic to be here and to be a guest on the show. I think the podcast is such a great idea.
Oh, great.
Thank you.
We're at this moment where quantum is, such a buzzword, but I think that there are so many listeners out there who are excited, both, those who are potentially just listening in as part of the public, who maybe don't know about quantum computing more than seeing it frequently, in different, headlines in the papers and in the news, and, really excited to get kind of an inside look of what's really happening, with the quantum computing revolution and why it could really matter, for general applications in the public. And at the same time, I think it's also a great opportunity for, for those who are at the forefront to really, hear conversations about, what's going on
now.
Get
some of that cross-pollination going.
Yeah, exactly. Some cross-pollination and some thoughts for the future as well. So I know I'm going to be tuning in, that's for sure. I'm looking forward to it.
Okay, great. Wow, I told you that closing bit on spectroscopic fingerprints of real world quantum computers, that just completely blew my mind.
Yeah.
I mean, it's almost like you're treating a quantum computer the same way that chemists and physicists treat, or run experiments on molecules and on stars and like reading their spectra.
Right.
But here, the experiment is, what are the operating characteristics of this quantum computer? I was just blown away by that.
Yeah.
It felt like, I mean, he's a physicist, so he doesn't talk this way, but in deep tech, we call that an awesome hack, right? I mean, that's just so cool. And it opens up a whole new frontier of a gigantic new vocabulary, right, of new performance characteristics for quantum computers. So I don't know. I thought that was a really cool perspective that, again, I just don't see widely discussed in many of the blogs, many of the social media feeds, or any of the popular press. So cool stuff.
Yeah, I mean it's a great example, Kevin, of what the argument is for building these NISQ machines, even when they can't do any useful computation, right? That's right. The question we get sometimes, the skepticism, which I think you and I actually hold, and I think is
necessary.
Valuable. Yeah. Right, exactly.
A lot of hype out there. Be careful.
We do not want to overhype these devices, but at the same time, we have to recognize that novel and powerful science is possible on them. And that science is very likely to play a role in the improvement of these devices to the point where they actually are able to do useful things. And that's, that's really the space that we want to continue to explore in this podcast. We're going to keep on trying to book future guests who can speak to both that what's the art of the possible in computation terms or computer science terms, as well as what are the challenges, and then the flip side of that, the physical sciences. What can we do with these things today, and what can we learn about our universe, and what potential productive value can we unlock before they're even useful computers?
I think there it is, man. That was a great episode. Thank you, everybody, so much for your time.
Yeah, thanks, and until next time.
Till next time, thank you now. Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.